Okay. So, we discuss about the filter bank analysis. So, output of a filter is nothing but a frequency parameter. That is why the filter bank analysis is called frequency domain parameter extraction methods. Now, design of those kind of filters has a little problem, means they are not that much of robust, because design an ideal filter of passband 0 to 100 hertz is very difficult. You know that in DSP, how to design this filter. Okay. So, instead of doing that, we try to represent other way. So, what is that? If you look at the slides, I am interested about this envelope only, the red line, because what you know, the speech is nothing but this is human vocal tract, this is HN, and there is a excitation En. So, En passed through the, so glottal excitation passed through the vocal tract produce the different speech event. So, I can say this is nothing but a SN, speech signal. Okay. So, different speech event, who is responsible to produce different speech event? HN. En, either En maybe excitation is present or excitation is not present. If it is excitation is present, then we call voice signal. If excitation is not present, there is a random noise, then we call unvoiced signal. So, there is a voice signal. So, the excitation is present and that excitation is same for all voice signal. Only difference is the shape of the vocal tract is different and different kind of speech signal is produced. So, our ultimate aim, find out the actual representation of HN from the SN. So, I recorded the speech signal SN, which is nothing but a convolution of HN convolved with En. Okay. Now, I want that how do I extract HN, eliminate En. I want to eliminate En. So, if it is a convolution, time domain it is a convolution. Now, if I take the frequency transform of this signal, so this is Sk, this is Hk, this is nothing but a multiplication of Ek. So, if I take the DFT here, discrete Fourier transform, or if I represent the speech signal in frequency domain, so this is nothing but a product of spectral representation of vocal tract with the spectral representation of source, excitation source. So, if I say excitation source is nothing but a impulse, then I want a speech or signal processing methodology by which I can separate Hk from the product of Hk into Ek. Okay. So, what I can do, if you see, if it is a product, if I take the log of Sk is nothing but a log of Hk plus log of Ek. So, I can take the absolute log or I can take the simple log also. Okay. So, in log domain, the product is nothing but a additive. So, if it is additive, then can I separate Hk from Ek, from product of Hk and Ek, from addition of log Hk and Ek. So, if you see, if this is a log spectra, that means after DFT analysis, I take the log, this is the log of Hk, this plot is log of, I have taken a signal Sn, frame signal, I take the DFT and after DFT, I what is get? I get Sk then I take the log magnitude or log of sk, log magnitude of hk. Then if I plot it, it will be look like this. This is a log, frequency axis is in log. If you see, I can show you. If you see, this is a linear view. So, this is the frequency scale is linear. So, here instead of taking the log, I find out that mod of sk and I plot that mod of sk with respect to frequency, that is spectrum. This axis is the frequency axis and this axis is the mod of x, which is root over of a square plus b square, because sk is in complex domain. Okay. So, I get this kind of response which is linear. Now, instead of plotting this, if I plot the log of this with the frequency, then instead of linear view, if I take the log view, so if I take the log view, I get this one. Now, if you see that I am interested about this envelope. So, envelope represent, if this slides envelope represent the Hn or Hk and variation represent the Ek. So, if I want to extract that, if I consider this is a signal, let us consider this log plot is a signal. So, there is a signal. If I told you that if you remember that suppose there is a sine wave, there is a signal which is high energy, high frequency signal, and there is a signal in pure sine wave. Okay. If I take the product of them, what I will get? The sine wave imposed will be the high frequency signal. So, now I want to extract this smooth version of the signal, this sine wave. So, I can see the sine wave is a low frequency component, this is nothing but a high frequency component. If this is my complex signal, so I can say if I pass this complex signal through a low pass filter, so low pass output will be the smooth variation of the signal and high pass output will be the high variation of the signal. So, I can say if I pass this spectrum with a low pass filter, this is considered as a signal and pass this through a low pass filter, then I can say the output of the low pass filter actually give me the envelope representation. So, that is my extraction algorithm. So, since I want to extract only Hk, so after log, if I pass this portion to the a low pass filter, then I can eliminate Ek, that is my target, and to find out log of Hk. This kind of signal processing has a special name. This is called homomorphic signal processing. So, this kind of signal processing has a special name which is called homomorphic signal processing. Okay. So, I am not explaining again these slides. So, I want a methodology by which I can deconvolve the convolved signal. So, this type of signal processing represent as a homomorphic signal processing. Now, what is LTI system? LTI system. LTI system means linear system. So, conventional linear system support the superposition principle. That means, if I apply L is a transform of xn is nothing but a L of x1n plus x2n, or if I apply every input separately and output can be added up, both will be same. That is the LTI system, superposition principle. Okay. So, if the signal fall in non-overlapping frequency band, then they are separable. So, suppose I have a signal which is nothing but a x1 xn is nothing but a x1n plus x2n, addition of two signal. Okay. Now, if x1n consists of frequency 0 to pi and x2n consists of frequency pi to 2 pi, then I can easily separate by a linear filter. I can easily separate. But if x1 is convolved with x2n, then it is very difficult to separate them. Or some of the x2 is overlapped with xn, then it is difficult to separate. So, what we want? We want, in principle of homomorphic signal processing, so importance of homomorphic system is the speech processing lie in their capability of transforming non-linearly combined signal to additively combined signal. So, basic purpose is that transform the non-linearly combined. So, I want that convolution signal can be represented by a additive signal. So, what kind of transformation I should do so that convolution become simple addition. So, if you see the slide, this figure represented the homomorphic system for convolution. So, xn some kind of transformation d, then it represented the, instead of convolution I get x1n plus x2n. Instead of x1n convolved with x2n, I want a transformation d star which will represent x1 x, so which may be the x cap n, which is in the form of x1 cap n plus x2 cap n, that I want. Then it can pass through the linear filter and I do the deconvolution inverse transform of this d, then I get the y. So, linear filter is that, suppose I want to extract this one. So, I can extract this one and I can inverse the inverse filter I can apply, inverse transform I can apply, I can get the x1. Okay. So, this is the purpose for homomorphic convolution. So, if you see this picture, there is a 3 part. First part, system take input, combine by convolution and transform them into additive output. Second part, system is conventional linear system, I can suppose linear filter. Inverse of first system, take the additive input and transform to them convolution output. So, whatever modification I will do in L part, linear time invariant, so those will be in additive signal. Okay. So, this is called canonic representation of homomorphic system. Homomorphic system. If I see this diagram for convolution, I can write a diagram for multiplication also. Okay. So, if I want that convolution should be represented in a sum form, then the system transfer function should be like this. Let us I take xn, okay. I take xn, I want that xn is nothing but a x1n convolved with x2n. So, at the end I want to find out the x1n, instead of convolve I want a x cap n, which is nothing but a x1 cap n plus x2 cap n. That is my target and this is my input. So, I apply this input. Let us take the Z transform, Z domain. So, let us Z transform. What I will get? At output I will get xz. So, xz is nothing but a x1z multiplied by x2z. Z transform of frequency domain representation, or I can say it is a DFT. So, I can get xk is nothing but a x1k into x2k. Then I take log. If I take the log, what I will get? I will get log of x1k plus log of x2k. x1k and x2k both are complex. Both are complex. Now, these things, so this is in k domain. Now I apply inverse Z transform or IDFT. So I get x1 cap n plus x2 cap n, which is nothing but a x cap n. So I can say this whole system can act as a D star, which is nothing but a homomorphic system for deconvolution. So if you see these slides, xn Z transform, so convolution become product dot, then dot becomes addition, then addition becomes addition. I take the inverse transform in time domain. So same things, whatever I do here, it is there in the slide. x1 n, then Z domain, then I take the log, I get cap, take the inverse transform, then I get the x1's cap into x2 cap. This is called Cepstral domain. If you see, it is not exactly xn. I taking this log signal as a time domain signal and take the inverse DFT. So this is not exactly xn. So this domain is called Cepstral domain. Cepstral domain. Now if you see, it is an additive signal. So I can say it can be passed through a low pass filter to, suppose I want to discard x2, that can discard x2, find out x1. So that x1 actually represent, so let's x1 is equal to nothing but a x1n is equal to hn and x2n is equal to nothing but a en. Then I can say I have removed en, whatever the x cap 1 n is present is represent the envelope of the spectrum. So x1 n is the spectrum of that envelope. So actually x1 n represent the time varying vocal tract. So that x1 n, those parameters, those can be used as a parameter which will actually represent the envelope portion of the spectrum signal, spectral signal. Okay. So this kind of homomorphic signal processing is used to extract the Cepstral parameters or called CC parameter. Okay, I will come. So this is the computational consideration. So if I say D star, DFT, log, either complex log or I can take the log magnitude. So if it is a complex log, then I call complex spectrum. If it is a log magnitude only, then I call real spectrum. So if it is instead of log, I can take only log magnitude. If you see these slides, if I see the only log magnitude, then I can, this is the real spectrum. If I take the complex log, this is called complex spectrum. Okay. This is called D star inverse, because I take the log, I take the complex exponential. So Cepstral analysis, there is a two kinds of Cepstral. One is called real spectrum, which is represented by a Cn, is called real spectrum, or it can be a complex spectrum, which is x cap n. If I only take the log magnitude part, then it is real spectrum. If I take the whole signal, this is a complex spectrum. So complex spectrum 1 by 2 pi x cap e to the power j omega j omega n, which is nothing but a log of x of e to the power j omega e to the power j omega. Have you understood or not? Log of this complex. So, this complex spectrum consists of phase and magnitude both, okay? And but real spectrum only the magnitude part, phase part is not there. Okay? So, in the end next day or one class I will take where I can say relationship between the complex spectrum to a real spectrum. That is, if x n is real, if my signal is real, then so if let us the signal is real signal, x n is real signal. Okay? So, if I say the spectrum log magnitude of the frequency representation of the signal x of omega mod part is nothing, is real, is a real part, and even thus the log of x of omega magnitude part will be also a real and even part of the signal. And if you know that x, if I take the DFT of this or I frequency transform ft of this, I can get x omega. X omega is a complex thing which has a magnitude which is mod of x omega and an angle of x omega a plus jb. So, mod. So, if I take the mod part, so mod part, if it is x n is real, this mod part is nothing but a real. So, if it is real, then it is has an even function, and if it is then if it is even function, if I take the spectrum of the take the log of this part, then whatever Cn I will get, spectrum I will get, this is nothing but a even part of the signal, and all the angle of that part, this is nothing but a complex part. So, this is nothing but a odd part of the signal. Okay. So, if x cap n is my real spectrum, then I can say the complex spectrum, then the real spectrum is nothing but a x cap n plus s cap minus n divided by 2. This proof I will do in the next class. Okay. So, this can be proved. Real spectrum is nothing but a complex spectrum plus x cap minus n divided by 2. Okay. Now, homomorphic filtering. Once what I said that this has to be passed through a filter to eliminate x to n. So, if I say this plane in Cepstral domain, so I said this signal treated as a time signal, and this signal is nothing but a frequency domain of that time signal. It is not actually frequency domain, or also it is not actually a time domain. So, I can say it is called Q frequency, Q frequency, Q E F R E N C Y. So, low Q frequency slowly varying component, high Q frequency fast varying component. So, removal of the unwanted component filtering can be attempted in Cepstral domain itself, and that filtering is called liftering. Instead of filtering, we said it is liftering, because this filtering of this here, this is not a time domain signal. Then this filtering called liftering. Okay. Then you can discuss the homomorphic filtering. So, if log x omega, then I can pass through a. So, in view of the time signal, I can pass the low pass filter, and I can find out the slowly varying component. So, I can say I am not going details of that the filtering technique of here. So, what are the steps to find out the Cepstral coefficient? So, basic processing step for frequency parameters, I get a x n is the signal. Then what I will do in the speech signal, I do the pre-emphasis to emphasize the high frequency component. Why it is required? If you see in the speech signal, low frequency are emphasized, but high frequency are not that emphasized. So, what I will do, first step, I will get a speech signal, let us Sn, I do the pre-emphasis. So, it is nothing but a, or I can say if it is Sn, so Yn is nothing but a, Here I have Sn is equal to Xn I have made, then I can say it is nothing but a 1 minus A into Xn minus A into X of n minus 1. So, that is given, and A value may be, or alpha value may be 0.5, 0.96, 0.5 to 0.96, 0.95 to 0.96 to 97, those are the variation. Okay. Then what I will do? I do the framing. What kind of framing? I have a speech signal, I put the window length, one window, red color to red color, one window, then I shifted the window, if it is 50% shifted, if it is 20 millisecond and 10 millisecond shifting, then 50% overlap. So, for each window, for each frame, I can get frame 1, frame 2, frame 3, and this each frame after windowing pass through a window. So, what I am doing? I just framing the signal, I am not doing the windowing there. Then after I cut the red to red, I multiply Wn. After I cut green to green, I multiply with Wn, which is window signal. Then what I will do? Windowing, hemming, Henning, cosine or rectangular. If I not multiplying anything, that means I am multiplying with 1, which is nothing but a rectangular window. Then I do the DFT. So, up to this process is convert Sn to Sk. That conversion has to be done. Okay. Then what we will do for power spectrum, for spectrum analysis, this Sk will be go to the log, then I do the IDFT. If I do that, then output is called complex spectrum. If I want the real spectrum, then what I will do, instead of Xk, I do another block here, which is nothing but a mod of Sk, then take the log. So, if I mod of Sk is omitted, complex spectrum. If I take the log mod, then it is called real spectrum. Then beginning, so then it can be passed through a low pass filter, that means beginning portion is a slowly varying component. So, those are called spectrum coefficient or spectral transfer coefficient, CC, or spectral coefficient. We can say the spectral coefficient. So, if I extract the, so whatever I get here, so after IDFT, I take the n length IDFT. So, k will varies from 0 to n minus 1. So, beginning component, all the beginning component will represent the slowly varying component. So, I can say let us C0 to, I can say C13, let us n is equal to something else, so C13 or C20, those actually represent the envelope. Those are called spectrum or CC, spectral coefficient, CC, spectral coefficient. Okay. So, basically this is done n by 2, because k equal to n minus 1 is not required, because DFT analysis is symmetry property. This is Fs by 2, you know that this is nothing but a n by 2. So, I can say k equal to 0 to n by 2 is sufficient. So, I can say take 0 to something, some length I can take which represent the envelope, spectral coefficient. Okay. So, this is the extraction of the spectral coefficient. So, what we have done, we are consider the spectrum has to be passed through a homomorphic signal processing, or what one kind of homomorphic signal processing we have done, by which we can extract the envelope of the spectrum, which is called spectrum. Okay? Thank you. So, next class we will discuss about the MFCC. Okay? Thank you.